Hi, in this video, we want to take a look at the chi-square test for categorical data. Okay, so the situation is that I have categorical data that I need to work with, and I want to analyze the distribution of my categorical data. So think about the situation where maybe I have data that's coming in red, blue, green. Okay, well, is the probability of red the same as the probability of blue, same as the probability of green? I want to know. I want a hypothesis test to check out the possibility that they have all the same probability, all the same frequency in my data. Okay, now let's take it one step further. What about the situation where I have two categorical variables and they're coming at me paired? Okay, well, in that situation, I want to know, are the two different variables, categorical variables, independent of each other, or are they not? All right, so if they're independent of each other, I can just treat each one separate. If they're not independent, then I have to work with both of them at the same time anytime I'm doing any type of work. Okay, and so, you know, this is stuff that we really want to know. The chi-square test is by far the most common test to be using in categorical data analysis. Okay, so first we're going to do a one-dimensional test, so I have just one categorical vector. Then we're going to transition to two categorical vectors where we have two levels for each of them. So we're going to end up getting a 2x2 table. And then we're going to kick it up a notch even further, where we go with two categorical vectors, and they can have any number of levels possible. We want to work through the details of that. All right, so let's look at a chi-square test with one-dimensional table, one dimension of data. All right, so let's say that I've got some data coming in, and here I just have, that is my vector of data that I've recorded. I've got red, blue, green, a whole bunch of different values. Okay, well, first thing I'm going to do once I get this data, I mean, it's hard to interpret the raw version. I'm going to convert it to a table. That way I get to see how many do I have of each one. All right, well, blue, we've got 8. Green, we've got 10. Red, we've got 12. Okay, so we see that we have different numbers throughout. It's possible that red is more frequent than blue, right? I mean, I would like to know that. Now, it might be that for the sample size, that's not much of a difference. It might be that that's a big difference. Right out the gate, it's hard to tell which one, which situation I'm in. Now, if I had a million data points, I saw one was blue, one was green, and all the rest were red, I would, have very strong evidence that red is more frequent. So the extreme cases are very obvious. So another extreme case is where they're all exactly the same. So if they're all exactly the same, I mean, it makes me feel very confident that we have the equal probabilities of each. It's in that gray region that I need hypothesis testing. Okay, so first and foremost, I need to state, what is my hypothesis? All right, I want to evaluate the possibility that the frequency of blue, the frequency of green, and the frequency of red are all equal to each other. My alternative hypothesis is any other situation than all equal. Okay, so remember that when we do hypothesis testing, equal signs always go into the null hypothesis. And here I'm going with all of them equal. All right, so when I say otherwise, that means that blue and green may be different. It might be blue and red are different, or it might be green and red are different, or we could have all three of them are different from each other. We don't really care how it turns out at this stage in the game. After I make a conclusion with my hypothesis test, then I go through and analyze more closely on the individual cells. All right, so it works out if I take the observed value minus the expected value, I square the difference, then I divide by the expected value, and then add it all up, I'm going to have a chi-square distribution. All right, so observed minus expected, square that, divide by expected of each cell, add it all up. That's my chi-square test statistic. All right, so this is coming from a chi-square distribution, which means I need a degrees of freedom For the one-dimensional version, it's going to be the number of cells that we have minus 1. Here we have 3 cells on our table, so therefore we have 2 degrees of freedom. O sub I is the number of observed values for the individual cell I. E is the expected value. All right, so now let's think about the hypothesis aspect. All right, so if they're all equal to each other, if the frequency of red is equal to the frequency of blue equal to the frequency of green, I would expect the observed value and the expected value to be relatively close. Okay, if they're relatively close, then this part of the fraction is going to be pretty small, and squaring it isn't going to make it that much bigger if it's already small. Therefore, if the null hypothesis is correct, I would expect to see a smaller value from this test statistic. So if the null hypothesis is correct, the observed and the expected should be relatively close to each other. If the alternative is correct, I would expect the observed and expected to be farther apart. When they're farther apart, that squaring makes it even bigger. And so what the alternative hypothesis will be consistent with a larger test statistic. All right, so remember, in hypothesis testing, if I see an extreme value away from the null, I go with the alternative. It takes extreme evidence to go with the alternative hypothesis. So if I see a big test statistic, I go with the alternative hypothesis. Okay, so first thing I'm going to do, and I strongly recommend that when you do your hypothesis testing, you draw the curve and then you shade it. This helps you keep it straight in your head as you work through the problem. So first thing I'm going to do, I'm going to draw the chi-square distribution by hand. I'm using a computer, so I'm not doing it by hand, but legit, honestly, I do this in real life when I do real hypothesis testing at work. I draw the curve, and then I reason through where is the rejection region. Well, big is where I reject. I shade the region on the right. Now, I don't have to be precisely correct. I just need a setup to help me reach the correct conclusion. So I shade a little bit on the right. Okay, so now let's dig in a little bit. Where is this cutoff? So remember, in hypothesis testing, I'm going to set a cutoff. Anything greater than the cutoff, I go with the alternative. Anything less than the cutoff, I go with the null. Okay, so I'm going to use a quantile function for the chi-square distribution. Alpha is my type 1 error risk tolerance. Frequently, it's 0.05. And this, I didn't display the code, but it's 0.05 for this example. Degrees of freedom for one-dimensional is number of cells minus 1. So 3 minus 1 is 2. And I want the right-hand side. Therefore, lower tail equals false. So what's my cutoff? My cutoff is 6. And I'm rounding off the digits in this display. So this is close to 6. All right, so now let's go ahead and slap down the cutoff. So the actual cutoff value is 5.991465 and a bunch of other digits. This is called 6. Okay, so now I have my distribution. I have my cutoff. What I need to do, I need to figure out, is my test statistic on the left of the cutoff or the right of the cutoff? So let's compute that. All right, well, if we say that we have all equal probabilities, then there's 3 cells, it's 1 over 3. So I'm saying my null hypothesis is the probability of blue is 1/3, probability of green is 1/3, the probability of red is also 1/3. Okay, well, the expected value then is just the number of observations divided by 3. So the expected value is 10 in each cell. Okay, so if I see counts that are far away from 10, that is evidence that I should go with the alternative hypothesis. If all the values I see are close to 10, that's evidence I should go with the null hypothesis. Okay, so let's compute the test statistic. I'm going to take that table of values. I'm going to subtract the expected value. I square it. I divide by the expected value, which is a constant, so I put it on the outside for computational efficiency. And then I'm going to add it all up. And so I can see my test statistic is 0.8. All right, let's take a look. Huh, look at that. That's nowhere near the cutoff. So here I will fail to reject the null hypothesis. So remember, when I reach my conclusion, I'm going to say it in terms of hypothesis testing, then I'm going to say it in terms of plain English. So I fail to reject the null hypothesis. That wording comes from the fact that I am setting up the situation, so I am prone to go with the null hypothesis, and I'm prone to not go with the alternative. You can see that by the amount of area underneath the curve over here. This makes it so that I'm protected from a type 1 error. So because I'm stacking the deck so much in favor of the null, we say that we failed to reject. Okay. So now I could also do this with R. I could just have R do the computations for me. Okay, so here what we're going to do, I'm going to use the chi-squared test in R. X is a numeric vector or matrix. Y is another vector. So if I have like two categorical vectors, I can put those in. Correct is a correction term when I'm using 2 by 2 tables. It's not applicable here. It's only applicable when I have 2 by 2 tables. Now, if I want to use specific specialized probabilities, I need to set my P. Here, this option gives me the ability to say, instead of P's, I'll give counts, or basically any non-negative values. And the P's get that vector gets rescaled to convert into a probability, if I choose to do things that way. We also have the option of doing a simulation with Monte Carlo if we feel like some of the assumptions don't quite fit for the standard chi-square test. It's not an issue in this video. And B is the number of Monte Carlo simulations. So here I'm going to take the table of my data. That's my X. Here, P is the hypothesized probabilities. Now I run the test. And look and see, I see 0.8 as my test statistic once again. Degrees of freedom are 3 minus 1. All right, so I can see that I got the same result, whether I did it by hand or whether I did it with the chi-square test. All right, so now let's kick it up a notch. Let's say now I've got two categorical vectors. They're coming in paired. And so I have, I want to know, are these two categorical vectors independent of each other? Do I have the same distribution throughout? All right, that is a spam call. All right, so to baby step it in, we're going to talk about the situation where we have two levels for each of these. All right, and there's going to be a special formula for this special case. All right, so I've got some data. I have color and I have letter in each of the columns. First column is green or blue. Second one is A or B. Okay, very simple situation in terms of our data. All right, well, in this format, that's my raw data. I can't look at this and analyze it. So first thing I'm going to do, I'm going to convert this to a table. All right, so now if I was to go through and count the number of times I have reds and number of times I have greens and number of times I have blues and number of times I have A and B and make a table, I can see that I get this table here. So 4, 5, 9, and 12. Okay, so now I want to analyze this. All right, well, things get a little bit tricky with this because what's going on is that we're going to say that my default hypothesis is that the frequency of blue and A is proportional to the row sum of blue and the column sum of A. My null hypothesis is that the frequency of blue B is proportional to the row sum of blue and the column sum of B, up and down. My null hypothesis in terms of green is that the frequency of green is proportional to the row sum of green and the column sum of A. So that's the proportional frequency of green with A. Now, my last null hypothesis is that the frequency of green B is proportional to the row sum of green and the column sum of B, or the column frequency, I should say. All right, so my null hypothesis is that all cell frequencies are proportional to their row's frequency and their column's frequency. Okay, so this is called the marginal frequencies. Okay, so what that says, this is what we would see if color and letter are completely independent of each other. We would see that more often than not, the frequency of blue and A would be proportional to the frequency of blue and the frequency of A overall. Okay. Now, by degrees of freedom gets a little bit more interesting. Remember that I went cells minus 1. Now it's going to be rows minus 1 times columns minus 1. 2 minus 1 times 2 minus 1 is 1 times 1, which is 1. So our degrees of freedom is 1 when we do a 2x2 table for chi-square testing. All right, so let's go ahead and I'm going to draw my chi-square distribution with 1 degree of freedom. And I'm going to shade the region to the right, because remember, if observed deviates from expected, then I'm more prone to go with the alternative hypothesis. So my rejection region is far to the right. Reject the null hypothesis in favor of the alternative if the test statistic is in the shaded region. All right, so let's go ahead and compute the cutoffs. So I know that my rejection region is to the right, but I don't know where is that boundary. So I'm going to use quantiles once again. I'm going to take dimension of the table, number of rows minus 1, number of columns minus 1, and multiply it together to get my degrees of freedom. My type 1 error risk tolerance is 0.05. And I'm using the quantile function. I want the region to the right. So I put lower tail equals false. And I can see my cutoff is 3.8. Okay, so now I know that this value is 3.8. Now, something that's very nice about the 2x2 table situation is that there is a formula that computes this very nice and quick for us. I've met people who claim that they can do this computation in their head, by the way. So what's going to be, if I have A, B, C, D are my counts, then my test statistic is total number of counts. So A, B, C, and D added up, the determinant of this table squared. Then I have column sum, row sum, and row sum on the bottom, and then we just compute it. So just to be consistent with this formula, I went through and worked at, assigned each of these the appropriate value for A, B, C, and D, and N, and here's my test statistic, and I see that my test statistic is really, really small. Okay, so let's go ahead and plot that. Like, wow, that is super, super close to 0. That's nowhere near the rejection region. I failed to reject the null hypothesis. So now let's go ahead and run this in R using the chi-square test. Now, if you remember, just a moment ago, I talked about a correction term. In general, if you're doing a 2x2 table, you want that correction term being used. I want to be consistent with the previous calculation I did by hand, which does not use a correction term. Therefore, for this example, for the purpose of the video, I put correct equals false. In real life, I will put this equal to true. So let's see what happens. I see I have 0.006, which I can see is 0.0065. So this 5 is probably it was probably 4 and then rounded up to 5. Here's my degrees of freedom. It's 1 again. So yes, we have consistent results with this. Now let's kick it up a notch even more. Now I want to deal with a much bigger categorical vectors, categorical vectors that have far more levels. So for this example, once again, I'm going with letters and colors. So letters are A through Z, colors are Roy G. Biv, and I have all these counts in here. I want to know, are letters and colors independent of each other? And I want to use hypothesis testing. Okay, so my null hypothesis is that all cell frequencies are proportional to their row's frequency and their column's frequency. All right, so that is saying that A blue its frequency is proportional to this entire row's frequency, A's frequency, and blue's frequency. Our test statistic is just going to be the same sum as we had before, but there's going to be more values in it. And my degrees of freedom use the same formula. There are sirens on the other side of the lake. I don't know if you can hear that. Okay, so for next thing I'm going to do, I'm going to plot the curve for the chi-square distribution with the appropriate degrees of freedom. Now you'll notice that this has a unimodal, and it's away from the y-axis because the degrees of freedom are much bigger. The entire distribution has shifted away from the y-axis. All right, and I know that my rejection region is to the right because that's consistent with everything we've been doing. I have the same formula for the test statistic. All right, well, degrees of freedom, I'm just going to take number of rows minus 1, number of columns minus 1, multiply. My type 1 error risk tolerance is 0.05, and I'm going to use the quantile function with lower tail equals false to find my cutoff. So my cutoff is approximately 180. If I see a test statistic greater than 180, I'll go with the alternative. If I see a test statistic less than 180, I will go with the null. All right, so the expected value is proportional to the frequency of the corresponding row and the frequency of the corresponding column. All right, so what I would expect to see would be row sums divided by n, column sums divided by n. That is the proportional frequency of each row, each column, multiplied by the total number of observations, which we can simplify down to this, and that gives me my expected value. In this situation, we are treating the row sums and the column sums as being like constants. All right, so now to compute all this out, I put a little bit of code in here. It's a little bit dense, but here's my overall table that we looked at a moment ago. I'm taking the row sums, I'm taking the column sums. I'm using this formula over here. I take the ith rows row sum, the ith columns column sum, multiply, and then divide by the total number of observations. That's my expected value for each cell. Now I subtract observed and the expected. I take the square and then I divide by the expected value. And then to top it all off, I add it all up together. In the end, I get 146. Okay, well, let's see how that looks. Well, 146 is to the left of my cutoff. I failed to reject the null hypothesis. Now, once again, I can run this in R, easy peasy lemon squeezy, which is what I recommend you do in real life. And we can see that my test statistic is 146, degrees of freedom is 150, which is exactly what we got before. All right, well, that's all I've got for you. Take care and goodbye.